Okay, and you've seen these like cheap lights. I buy these like, you know, after the holidays. They're on sale, like really, really cheap. Ooh, I can use these to like light up the podium and make it look all festive here. Excellent. So these are a series circuit. There's a whole bunch of light bulbs that are connected in series. How can I tell it's a series circuit? Well, if I take one light bulb and I pull it out of the string as a whole goes out. And that's how I know it's a series circuit, because when I pull that one bulb, now there's basically a hole in the circuit. There's an open circuit. No more current flows. Okay? So it's a series circuit. And you might say, well, that seems like not such a great idea. That's not such a great idea, because then if you lose one light bulb out of the circuits, the string as a whole goes dark, and that's not so good. But there's two extremely good reasons for making bulbs this way. One is it's cheap. And it's cheaper just to go from bulb to bulb to bulb to bulb, okay? To do a series circuit. It's much cheaper than doing a parallel circuit. But there's another reason, and that's this. There are 50 bulbs in one string. And so the circuit as a whole looks like this. I have my household electricity, which is 120 volts, and it's connected across 50 bulbs, which are connected in series with each other. And what's the voltage across each individual bulb in the circuit? Well, the voltage across each bulb, since they're connected in series, they're going to share that. They're going to split it. So it's 120 volts divided by 50. And so you end up with 2.4 volts across each bulb. And that's a good thing, because if you have lower voltage, there's lower voltage across each one of those openings. And lower voltage bulbs, there's a certain safety factor here. And so they tend to be cheaper, but they're also safer. Now, you know strings in, or bulbs in strings like this can go dark, okay? You can have a bulb, and it can go out. And if the bulb goes out, the string as a whole doesn't go dark, right? But if I pull a bulb out, the string does go dark. So what's that about? Here's what it's about. I'm going to take a bulb, and I'm going to pull it out of the circuit. Okay, and if I do that, the circuit as a whole goes dark, because now there's no current in the circuit. Okay, so I have my bulb here. And now the circuit, I've taken one bulb out, and so now it looks like this. It's like bulb, 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 dot, 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 bulb, open part in the circuit. And there's a place where there's a bit of a break here. Okay? Now here's my question. How much current is flowing in the circuit right now? Of all these light bulbs. There's zero current in the circuit. What's the potential difference across each one of these light bulbs if there's no current? Zero. So what's the potential difference across this break in the circuit? 120 volts. 120 volts across that break in the circuit. Now, if you were to take one of these bulbs and drop it on the floor, oh, and all of a sudden we step on it. Oh, no, and the bulb is completely broken, and I didn't learn my lesson, and I smashed it really bad this time, but I think not so bad that I can't get it in. How much voltage is across the gap? 120 volts for the bulb was in the circuit. And when I put the bulb back in, here's what happens. It's got 120 volts across it. And for just a second, it's got 120 volts across it. There's a little shunt in the base of the bulb. There's a little piece of semiconductor material. And when it has 120 volts across it, it basically fries and turns into a resistor. It's an insulator, but when 120 volts is across it, it goes, bzz, turns into a resistor. And then it turns into a little resistor that's the same resistance as the light bulb filament. And so it can carry the current. Even if the filament's broken, it'll continue to carry the current. So the bulb can burn out, the filament breaks. And when it does that, there's a momentary cessation of current, but there's 120 volts across the gap. The little semiconductor piece goes, bzz, turns into a resistor, and then the current picks up again. So it's sort of it's a cool little thing about the way these lights go. They're very, very clever, because it used to be, it's one of those back when I was a boy stories. Oh, yes. I mean, we had to go, if a bulb went out, then you had to go figure out which one it was, and you had to take them all out. And if two of them went out, oh, heavens to Betsy. The holidays were in serious danger. I mean, it was a problem, and now we have these it's a clever solution for that. Let's look at a couple of other warm-up exercises, and I want to start with this one. The diagram below shows a segment of a circuit. What is the current in the 200 ohm resistor And we're going to say that as a group, okay? We're just going to answer as a unit. It's 2.5 amps here, 1.5 amps here. How much is in the 200 ohm resistor? 1 amp. And you know that because you've just said, oh, okay, 2.5 amps comes into this junction, 1.5 amps goes out. How much goes this way? 1. 1 amp has to go that way. That's Kirchhoff's junction law. Now let's look at an application of Kirchhoff's other law. The diagram below shows a circuit with 2 batteries and 3 resistors. What is the potential difference across the 200 ohm resistor? I want you to talk to your neighbors about this. I'm going to call a name out of the box and ask you to tell us what's the potential difference across the resistor and how you got there. How did you calculate that? What do you think? 2. How do you get it? So I got like 0 volts here, 4.5 volts here, 7.5 volts here, and you have a 3 volt, not used up, but a 3 volt drop across there, which takes us from 7.5 down to 4.5. And then if I drop by 2, I'm down to 2.5, and I go another 2.5, and I'm back down to 0.